Hello everyone, it's Steve with Aptera Owners Club. Aptera released this battery validation video a few days ago. Thought it was very interesting. I love it when Aptera puts out tech videos, and this shows some actual, real progress towards getting the production out. This looks like this should be the production battery pack. The cells are not. I don't think that these are the production cells, but they are similar commodity cells, and we'll talk about that. But this design and the way it's being put together is the production battery pack, and they are validating it. So let's watch it together and then talk about the details of it.
Hi Aptera fans, Tim Vaughn here.
Okay, Tim Vaughn is the guy from Flux Energy. So I don't know if he left Flux Power battery and moved over to Aptera, or if he's kind of just doing both jobs at the same time, because he's one of the chief battery guys over at Flux Power, which is the lithium iron phosphate. They do mostly stuff for forklifts, and that was a company that Chris Anthony helped start a while back.
I would like to give you an update on the latest going on with our battery pack validation and some details about the unique elements to our battery modules. First, let me give you an overview of our battery module. It's made up of battery cells, current collectors, and a circuit board that talks to our battery management system. This is a cylindrical cell. It's called a 21700.
Okay, so 21700, that basically talks about the form factor. And if you look here, it gives you the dimensions of it. Let me see here. This will give us dimensions, I think. Right here. So the diameter is 21 millimeters. So diameter is 21 millimeters across, and it's 70 millimeters long. So I don't know why it's 700 instead of 2170, but that's just convention. They add the 0 at the end, so it's 2170. So if you look at like the 18650, that means it's 18 millimeters across and 65 millimeters long. If you look at like the 4650, that means that is 46 millimeters in diameter and 60 millimeters in length. So that number defines the size of the battery. So it's 21 millimeters this way and 70 millimeters this way.
Cell, and this one has a chemistry in it that's referred to as NMC, nickel manganese cobalt.
Okay, so NMC, nickel manganese cobalt. Let's see here. If you want to talk about that, that just refers to the cathode chemistry. So the cathode is 80% nickel, 10% manganese, and 10% cobalt. And this is the older NMC batteries were 622, so 60% nickel and then 20% manganese and cobalt, respectively. They want to reduce cobalt content because cobalt is the most expensive and hardest to get part of that thing. Nickel is easier to get, and manganese is a little bit easier to get. Cobalt is what they're trying to reduce, and NMC 811 is the more common NMC chemistry. The anode is usually graphite or silicon graphite, most likely silicon graphite, I'm guessing, because that is the slightly better anode at this point. So the cathode is nickel, manganese, cobalt in a ratio of 8-1-1, so 80%, 10%, 10%. And I think this is like thermal compound he's putting down. That's the cooling plate is down here, well, the cooling plate will go down at the bottom, and then this is, I think, thermal compound to help transfer the heat down the bottom end of the cell to the cooling pad and the thermal regulation system.
That results in the higher energy density storage that's possible in battery systems like this. Each module contains 384 of these cells.
Okay, so 384 cells. So let's remember that.
Providing 7.3 kilowatt hours of energy per module. Launch edition vehicles will have 6 modules.
All right, so let's repeat that again. So
launch edition vehicles will have 6 modules, 3 kilowatt hours of energy per module.
7.6 kilowatts, I think that's what he said.
Providing 7.3 kilowatt hours.
Okay, 7.3 kilowatt hours. Okay, so let's look at, you remember that Aptera announced back in June of 2022 that Eve Energy was going to supply the cylindrical cells, the NMC 811 cylindrical cells. That was back in 2022. I do not know if this is still the supplier. You know, a lot of things have changed. Battery prices have come way down since 2022. Commodity prices of nickel, manganese, and cobalt and lithium, they've all come down since 2022, which is good. So the battery packs are likely to cost much less than expected. Other things may have gone up, but the battery prices have definitely come down. And so I don't know if Eve Energy is still the supplier, or maybe Aptera found a cheaper supplier, but they haven't announced it yet. Or I think more likely Eve Energy is still the supplier and they are reducing prices to kind of match the market movement of it. So anyways, that's what they announced back then. And so if you look at, I looked up Eve Energy's NMC 811 21700 battery cells, and I found two types. There's this type, which is the 4 amp hour one, but this one has higher discharge and charge rates and slightly better thermal performance. This one has more capacity and higher volumetric and gravimetric energy density, but slightly lower maximum charge and discharge rates and slightly worse thermal performance. I believe they're going for this cell, the higher capacity cells, because let's look at this. If you look at the energy per cell, it's 5 amps times the nominal voltage, 3.65. Okay, so if you look at that, that's 8.25 watt hours per cell times 364. That gets 7,000 7 kilowatt hours per battery pack. And he said 7.3, right? Let's go back.
Each module contains 384 of these cells.
384. Okay, so my bad. I did that wrong. So let's go back. 3.65 times 5. That's 8.25 per cell times 384. Oh no, I did put that down.
Providing 7.3 kilowatt hours.
7.3 kilowatt hours. So I think maybe he's using higher than nominal the nominal voltage to do it, but definitely you would not get that with the 4 amp hour cell. Or perhaps there's a new cell that's not showing up that has slightly higher capacity. Maybe it's 5.3 or 5.2 amp hours. I don't know. But I think that's generally how we get to that number.
Hours of energy per module. Launch edition vehicles will have 6 modules, resulting in a 44 kilowatt hour battery pack.
Yeah, so if you multiply this times 4 times 6, you get 42. But if he's saying 7.3 times 6, then you get 43.8, which is close to 44.
This is an example of one of our current collectors. This one in particular gets welded to the top of each cell.
Okay, so this is the current collector, or what many people call the bus bar. And if you look at this, what you see here is this is going to connect to the cathode, so the positive, and this end's going to connect to the negative, the anode. If you want to go back to look at one of these cells, okay, that's not a very good picture. Let's look at this picture. So the cathode is right here, and the anode is at this lip and all the way around. So everything else is the anode. So you can actually connect to the anode at the back end of the battery cell, or you can connect to the anode right here at the rim, and the cathode is right here. So positive is right here, and negative is right here. All right, so yes, so you can see that's how it ends up. And then we're going to take a look at this bus bar. So this, they put out this Twitter image. No, that's not it. This one. They put out this Twitter image a while back, and you see the bus bar. You see right here, this is a single current collector. You see this is all one piece right along here, or maybe this one's a better one to look at. So it's all one piece here. And if you look at this, On this side, it's connected to the cathodes, the positives on this side. And then on this side, it's connected to the negatives over here, here. And then if you swing across here, it's here and here. So basically, these two rows are hooked up in parallel, and then it goes over to series to these two rows. And if you count this, this is 12 across here, so 12, 12, that's 24. So 24 in parallel, and then it goes across. So we can figure out the arrangement of this battery pack. So he said there's 384 cells per pack, and then you divide that by 24, which is how many are in parallel. And then you find out it's 16. So what it is a 16S 24P battery pack. And so if you take 16 and multiply it by the nominal voltage, you get a voltage that's 58.4, so around 60 volts. If you go by its maximum voltage, fully charged voltage, which is 4.2 times 16, you get 67 volts. So they're calling it a 60 volt system, but nominal voltage is 58 and maximum voltage is 67. So I think that's the voltage. And then if you multiply this times 6, that's a 400 volt system. So the 400 volt system is the maximum voltage, 403 volts. And so they're getting 6 of these modules and putting them in series to get the voltage numbers. All right.
The cells.
But again, this arrangement is really nice. This looks really good. I made a video about this when this picture first came out, but compared to like Lucid's battery pack, it looks a lot better. And it looks very similar to Tesla's new bus bar design for their 4650 cells, the battery packs using the 4650 cells. You see how like these things click into these little plastic tabs, and then that perfectly positions these things to be tab welded very quickly. And so I think this makes it very, very easy to manufacture this pack. You just like drop the cells in, snap the bus bars in, and the bus bars come in and they're guided in by these little plastic pegs, so they line up perfectly, and you just put it on a machine and bam, 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 it just like tab welds these very, very quickly. And so I think this would be like really easy to manufacture, and it's very, very well designed. Okay, let's continue.
In the correct location so that when the laser machine or wire bonder or anything like that comes down, it's a predictable location, and that machine can then attach the current collector.
Yeah, so you see like this is before, there's no cells in this. They just put this on there, and you see it's put on these little guides. But you can see how like when you put the cells in there, the cells will perfectly fit right here so that both the anode and the cathode of each cell can be welded very quickly
to the top of the cell, either to the anode or to the cathode. And that's done with groups of parallel cells across the module this direction, and then those cells are welded in series in this direction.
Yeah, so there's 24 right here, and each group of 24 is put in parallel, and there's 16 groups of 24 in this pack.
So from the first group of 3 or 4 volt cells all the way down 16 groups later, you end up with about a
Okay, so yeah, there you go. He said 16.
60 volt module. Our module design is inherently flexible in that it facilitates multiple cell connection approaches, including laser welding, wire bonding, and ribbon bonding. It also is adaptable to cells from multiple suppliers, thereby reducing future supply chain risks.
Right, so you can get these cells from Samsung, LG, Eve Energy, it doesn't matter. They're all like 21700 cells are commodity cells, and you could easily replace them out. So, you know, you see like this one is a LG cell, and they're very similar. This one has a nominal capacity of 5 amp hours, just like this Eve Energy has 5 amp hours. Nominal voltage is 3.65. Nominal voltage of this is 3.63. So very similar. So they could just swap out these NMC 111 cells into this battery pack, no problem.
This is an empty module. There are no cells in it. If there were, it would be very difficult to lift. This module sits in this aluminum frame. The particular frame you're looking at here is a prototype that's slated for one of the early PI builds.
Yeah, so what I don't know is if this is the prototype, I don't know if this is the production intent design of the battery tray. This looks like it's prototyped, like hand built and hand welded. I believe probably the real one for the large scale production would be forged. That's my guess. And then you wouldn't have any of these welds and stuff. It would just be forged in one piece, maybe.
And these modules are bolted into the frame, and they rest on a cooling plate or a heat exchanger plate that allows us to take heat out of the module or warm the module in cool environments. Finally, the circuit board.
Right, so they're planning on, as you can tell, they're planning on active battery thermal management. They will pre-warm it so that it works better in cold weather, and also they'll pre-warm it so that if you want to come up to a fast charger, it'll be ready to take the fast charge. They'll precondition the battery thermally, and then of course when you're discharging it and it gets hotter, they can cool it down as well. And so they're doing end cooling. You can see that there's no space in between the cells to do side cooling. The very early Tesla battery packs use side cooling, and they use this like serpentine coolant path between the cells, but Tesla has, I believe, moved to end cooling as well, and I believe Lucid also does end cooling, and Aptera is going to do end cooling, and that gives you greater density of the battery pack.
Our team calls this the MIB, or Module Interface Board. This is the interface between the high voltage modules and the battery management system and the rest of the vehicle. You can learn more about Aptera's battery management system in the video by Andrew Stanton after this one. Now let's get to the ongoing validation work. Our battery module was subjected to aggressive vibration and shock testing over a 3-day period at a local laboratory called NEMCO Testing Laboratory. This highly accelerated lifetime testing represents...
And you can see here that there's foam in here. So after they put the batteries in and build it, they encapsulate these battery packs in foam. If you've ever seen the battery breakdown videos on like Monroe's channel or anything like that, you'll see that it's just filled with foam. There's like polyurethane foam and EPDM foam. There's many different kinds of foams, but the foam is there to like thermally isolate cells in case one cell gets too hot or starts having thermal runaway, and it's for safety reasons, and also it's to reduce the vibration, so it kind of like buffers the vibration. And so they're testing vibration here.
100,000 miles of vehicle use. The results are in. No mechanical failure occurred, and all electrical performance was unchanged. We also performed microscopic inspection, confirming no damage or signs of wear. Thorough electrical testing was also performed after the mechanical testing, and this confirmed that the module has experienced no capacity reduction or other electrical failure. Early testing also suggests that we can charge at a rate well above 400 miles per hour. This means...
So that's very impressive. Like the charge rate is very, very good. 400 miles per hour is pretty awesome. And you saw the foam in there, and I think they don't talk about it here, but I imagine that they're going to do like thermal testing of the battery pack, as well as like water vapor intrusion, that kind of testing. That seems like that would be pretty standard testing for these battery packs.
We're full speed ahead building modules for our PI vehicles. I'm confident with our battery module design, and along with the rest of the Aptera team, we're excited for the next few months of accelerated progress. Until next time.
Okay, so that's pretty awesome. Again, I think that Aptera's battery pack is like very well designed and very well designed for manufacturability, and the bus bar design I think is quite nice. And the way that it's just engineered well, and hopefully they're going to be doing a lot more testing. They've done the vibration testing, but I think they need to do thermal testing. And make sure that the coolant pads that they've put on can cool the battery pack efficiently when it's being discharged at a high rate and being charged like fast charging. And they probably need to do some like intrusion testing onto there with like water vapor or maybe even some water. Make sure that it's stable in those ways, and then thermally cycle it, putting in very cold and very hot conditions as well. But I'm sure that they're doing all that because they know more about batteries than I do, obviously. Um, but yeah, very very good progress. Let me know what you guys think in the comments below. Thanks for watching. Have a great day.